and thank you for taking the time to join us today for this exciting webinar being brought to you by Cintiq Instrumentation. My name is Tanya Coulthard, and I will be your host as well as one of your presenters for today's webinar. Our webinar today is entitled Introducing the NGbr, a disruptive 4D bioprinting system, a detailed review of 4D bioprinting applications using the NGbr system. This is the second webinar in our three-part series introducing the NGb-R system, as well as Cintiq's newly formed partnership with Poietis to distribute the system within North America. Today, we will have three presenters, myself, as well as Antoine Jacot and Michael Garcia, both from Poietis. We will each do a quick introduction to ourselves before each section within the webinar. During the webinar today, I will give a brief introduction to the NGb-R system as a bit of a recap for those who were unable to join us on the first webinar. Michael and Antoine will then take over and go through some really exciting applications with specific examples and images of how the 4D bioprinting can be used across a wide variety of applications, some of which are quite unique and emerging within the bioprinting world. Before we begin, though, I'd like to briefly mention a few housekeeping items. We do anticipate that today's presentation will be about 45 to 50 minutes. This should give us some time at the end to answer any questions that you may have. So please use the Q&A dialog box throughout the presentation to ask any questions that you have that you've thought of during the presentation, and we'll do our best to get through as many of those as we can. As with the first webinar, when we had a tremendous amount of questions, we will create a transcript for the questions that we do answer during today's webinar, but also those that we're unable to answer. And we'll send that out to everyone over the next few days. Please also note that today's webinar is being recorded. So if for some reason you lose connection or you can't hear anything clearly, you will have access to the file to review later. And at this point, without further ado, I'd like to get things started. So as I mentioned, I will be one of the presenters today. I manage the imaging division here at Cintiq Instrumentation. And as discussed in more detail in the first webinar of this three-part series, Cintiq and Poietis formed a relationship back in January, allowing Cintiq to distribute the NGb-R system within North America. Cintiq's headquarters are in London, Ontario, Canada, but we have offices in Texas as well as in the Netherlands. Poietis, the manufacturer of the NGb-R system, is located in Bordeaux, France. So for today's webinar, we'll start with a very brief overview of the system to help those, again, to understand a little bit more who weren't able to attend that first webinar. I will then hand things over to Michael and Antoine, and they'll walk us through a few applications, focusing on specific ideas as it relates to some of the hardware of the system. For example, looking at soft tissue models that use the multimodal printing capabilities of the NGb-R system. Moving then to talk more about the chip type arrays, like organ on a chip or microelectrode arrays, which require the integrated microscope and the ViewPrint software. Finally, they will walk us through some of the examples of high throughput screening assays, which with a focus more on the requirement of using the laser assisted bioprinting capabilities of the system. Finally, I'll rejoin the discussion as we work through the questions during the Q&A discussion. So again, please feel free to answer any questions that you have in that Q&A dialog box. And again, I'll work through them with the team. And if we don't answer them, we will get that transcript out to you towards the end of probably into next week. So to start things off, I'd like to run our first poll question. And so for those of you who did join us on the first webinar, the questions are going to look really familiar. We are hoping that we'll have quite a few new participants in the webinar this time, so we'd like to get a little bit more information about if you're using bioprinting in your work currently. And if so, maybe a little bit more about the techniques that you're using, and then also understanding what type of research or work that you're actually working on, just so we can have a sense of if people are in the basic science world, more looking at translational or regenerative medicine, or even into the cosmetic and in vitro testing. So I'll give everyone just a couple more seconds to respond to that. Perfect. Thank you for taking the time to answer those. So at this point, I'm going to, again, just do a really brief introduction to the system. So during the first webinar, we went through a more detailed overview, but I did want to answer a common question of what does NGbr stand for? And it stands for Next Generation Bioprinting. And this system is specifically their research-based system, as Poietis is currently working on developing a clinical platform as well. So that's where the R comes from. As you can see in this video, the NGbr is a standalone system. It does include a biosafety cabinet, a BSL2, to allow you to prepare your cells, all of your bioinks, and your material and media that would be needed during the bioprinting steps. The onboard computer allows you to take the specific cell patterns that you would design on the CAD software, integrate them into the fabrication process, set up all the different steps that you want to take place. And then finally, the robotic arm is going to take over, and we'll see that in action in the next slide. But basically, that robotic arm is going to carry out all of those program steps that you use that onboard computer to process. So here we see the system in action. So as you can see, once the programming is complete, the automation of the NGbr takes over and provides operator-independent workflows. This allows for very high reproducibility of those fabrication steps and a very tight control over the resolution and the spatial distribution of the designed cell patterns that you would do in that CAD software. In the center of the instrument is this robotic arm. Just let me turn on my laser for us. So you can see the robotic arm in the center. This is an industrial grade robotic arm with very high precision. So it's moving the plate around between the different printing heads. So we have the laser bioprinting head in the middle, and then we have three different heads which are optional. So you can include different extrusion or inkjet heads here to allow you to print collagen and other extracellular matrix compounds as well. On the side here where we see the instrument right now is actually an integrated microscope, and that's going to take a picture at whatever steps you program to allow you to see at a microscopic level what's going on with the cells and the materials that are being printed. There is a shield, it's a glass shield with a film on it to prevent any laser light from escaping from the system, and there's an interlock to ensure the safety of the operators there. So with the overview of the system hardware complete, I do now want to turn things over to Antoine and Michael to walk through some of the really interesting examples that we have for you today and how a wide array of research areas can benefit from this type of a technology. So Antoine, I'll turn it over to you.
Yeah, thank you very much, Tanya. And I must say that it's a real pleasure for both of us to meet again today. So for those of you attending who were not with us last time, my name is Antoine Jacot. I'm sales manager at Poietis. So basically, I'm looking after the NGbr product line and helping the company bring this amazing technology to the market. Today, however, we're not going to discuss the instrument again, but rather we're going to focus on the different possible applications enabled by some of its key features, right? So we'll try to throw in as many as possible today, although 45 minutes is not going to cut it. So it's not going to be enough time to cover them all. So with NGbr, from producing tissue and organ models through cell patterning, all the way to distributing cells at very specific spots onto custom-made chips, devices, or 3D scaffolds, the technology makes it possible to work on an outstanding collection of advanced tissue engineering applications on many different levels. So that's including translational medical research, RegMed, oncology, high-throughput studies, and even pharmacology. Just before we delve into some of these, though, I'd like to give you a very quick recap on the laser-assisted bioprinting technology, as we have received a ton of questions about this last time. So laser bioprinting is a unique nozzle-free technology that has this capacity to precisely distribute cell droplets spatially according to specific and tailored micropatterns designed to help guide self-organization of cells. And that is with a speed of up to 10,000 droplets per second and an average cell viability ratio of about 95%. So really outstanding specifications here. So with this technology, there's actually no need for conventional bioinks. What I mean here is that cells can actually be printed directly in culture media. So typically from 8 to 15 microliters of this cell media is deposited directly over a golden metallized substrate called a ribbon, and then spread it across its surface. So cells will then be printed against gravity from the bottom up into a receiver of your choice. Now, a lot of people are actually interested in working with several different cell types and often wonder what options they have with NGbr, right? So let's take an example here with, say, a couple of them, so fibroblasts and immune cells. The first question is, do you actually need a specific pattern and bioprinting location for each cell type? Because if you don't, then a single ribbon approach might suffice, right? Here, both cell types are going to be mixed out on the laser ribbon and can be printed together with one same pattern. However, it's usually the case that each cell type is to be distributed separately in a precise way and at a specific location. So then it's highly recommended to have a dedicated ribbon to each cell type. That's totally possible. And this approach allows to work with very different micro patterns and perfectly fits with a specific, say, layer by layer protocol. There's a third option, though, which consists of relying on different bioprinting modalities. So that's another advantage of working with a multimodal platform like ours that features not one, but three simultaneous technologies. And that is that one cell type can be printed with the laser head, while another cell type could be printed with, say, a drop dispensing head, for example. So there's no limit in terms of a number of cell types or micro patterns that one can work with. Last but not least, so the laser bioprinting technology is compatible with a great deal of cells. We've worked with primary human cells, but also embryonic and pluripotent stem cells. And we even have a team currently working on plant cells very successfully, so protoblast. In total, that's about 26 different cell types that we've tested, and all of them with a pretty good viability ratio. So Mikael will tell you more about this later. So now let's delve into those 4D bioprinting applications that we've discussed and start with those made possible with a multimodal instrument, boasting not one, but several bioprinting technologies. For those of you who attended our last webinar a couple of weeks back, you probably remember this slide. So that's a typical scaffold-free soft tissue 3D biofabrication workflow with the instrument, printing layers of cells with laser bioprinting and layers of ECM with microvalve. And here is the same workflow, but tracked with the onboard microscope in the instrument. Laser bioprinting has this, genuine advantage of allowing for very precise positioning and for a specific pattern to be maintained across many layers, which is really interesting here. So here is the first example of this multi-technology biofabrication approach in action. And this one was used with bioprinted full skin models by BASF. So that's a German-based and also the largest chemical company in the world, which we partner up with. And we're interested in testing and evaluating new compounds. So in this example, new active ingredients for an anti-aging peptide complex. Bioprinted tissues are a great alternative here to, say, animal testing in cosmetics and dermopharmacy. But above everything else, these in vitro tissues could prove, the efficacy of a specific ingredient over collagen synthesis, for example, and overall improvement of skin structure. So we have taken BASF's manual protocol and translated that into an automated one with the NGb-R platform. That's exactly the kind of support that Poietis can offer to customers. So the workflow consisted of the following. It all starts with in vitro assays that involve several cell types, so here fibroblasts and keratinocytes, that are then bioprinted to form an actual full skin model on which new compounds are tested. And that followed by in vivo clinical studies on both animals and in human beings. So with BASF, the effects of a couple of active ingredients were evaluated, so AT11 and AT9. These compounds were incorporated into bioprinted skin models and left for maturation for 3, 4, 6, and 9 days. Both of them proved to increase collagen synthesis in both fibroblasts and keratinocyte cells, as well as syndecan and lumican on the reconstructed skin. So here you can see the actual treatment. So after what we've just seen, the whole anti-aging peptide complex, so basically the combination of both tetraploid ingredients that we've seen before. So the whole mix was evaluated through confocal microscopy, following a 15-day long daily treatment on reconstructed 3D bioprinted skin. And what they observed is that a well-defined network of intense collagen fibers was there. So as illustrated here in these pictures and video as well, this anti-aging peptide complex significantly improved both the density and the organization of the extracellular collagen fibers in the bioprinted dermis. And so that was made possible with, again, just a 3D bioprinted tissue model. So after that, the peptide complex was then taken on to clinical studies with eventually a trial on human beings. That's really fascinating work. So following a 56-day-long daily treatment, so after 56 days of a daily treatment, we observed a visible wrinkle reduction efficacy of the complex, and especially a clear correlation between the collagen increase that we observed with the 3D bioprinted skin models, as well as these clinical study results. I'm going to move on to another topic now, although there's a lot more to be discussed. But if you guys want to find out more about the methodology and results, there's a couple of publications that we've done with together with BASF. So feel free to ask us in the comment section for these publications if you'd like to read them. Here's yet another example of this multi-technology layer by layer tissue biofabrication protocol, but this time with liver cells. So this comes from another partnership that we've had, this time with Servier Labs. That's a leading French pharmaceutical group, to produce 3D liver models so as to help them detect possible drug-induced lesions in preclinical phases. So these are pretty rare, but can have some very serious consequences for patients. The problem is that certain drugs' hepatotoxic potential is quite poorly detected with the model that we currently have, so the current preclinical models. Those are usually based on human cell cultures, and they tremendously lack longevity, complexity, and of course, well, that's quite a limiting factor, isn't it? So 3D bioprinted models can help overcome these limitations with the advantage of, again, avoid animal models. So we've used the laser bioprinting technology here to distribute, organize, and pattern different cell types, including hepatocytes and hepatoRG cells, towards a much more complex model, right? That's the idea. And so the tissue contained lines of human liver cells as well as immunocompetent cells within a specific architecture that is, of course, designed beforehand. And that's designed to imitate human liver tissue in vitro. And here's an immunostaining of human hepatocyte post-printing, showing cell expression as in their endogenous nature, proving that the approach is successful in replicating, mimicking organic liver tissues, because, well, that's the whole point of bioprinting, is we want to be able to replicate and mimic as best as possible organic tissues in the first place. Now, I'm going to move on again to another kind of application, but just before I do so, one more comment here. This approach, so this layer by layer multi-technology approach, can be applied to a very high number of cell and tissue types, right? So from cardiac to pancreatic, to name a few. So we won't have time to present them all, unfortunately, But the technology is, of course, compatible with a lot more applications here. So moving on to onboard microscopy here, that's another application field that's quite unique to NGbr, because what follows is based on microscopy, of course. So many people often ask us, hey, what's the interest of having a built-in onboard microscope inside the bioprinting platform? So we thought it would be really interesting to give you uh, a thorough answer to that, but with illustrated application. So here it is. This feature here is called ViewPrint. That's actually a really cool tool that allows the user to visualize the receiver through microscopy ahead of the printing, and to select one or several specific spots for cells to be distributed into. So here's how it works. First, well, you're going to have to launch ViewPrint, and then just easily move to the area of the receiver that your fingertip, right on the NGb-R touchscreen interface. So there's a computer that comes with the instrument, of course. There you may select the spots for cells to be printed in, and simply let the system do its job. And then, well, just use the onboard microscope again to visualize bioprinted cells, more as a quality control tool. But all this can be done while maintaining full control over resolution. So what I mean here is that the actual volume of cell media printed and the number of cells distributed into each spot can be controlled with the laser bioprinting technology, and that's really beautiful. Now, limits and advantages of ViewPrint. Of course, for full patterns of cell droplets, so an entire grid of, say, 200 to 400 droplets, ViewPrint is definitely going to be time consuming and not the best choice. So we'd highly recommend, of course, to rely on the powerful cell patterning tool that comes with Poietis's CAD software. But ViewPrint can prove a fantastic tool if you're interested in incorporating a secondary cell type, for example, or only a few drops at very specific locations of your choosing. So let's take another example. We've got some experience with this. Here, we actually needed to distribute mesenchymal cells into a selection of wells across a collagen-coated microgrid array with very high precision. And I'd say that the key word with ViewPrint is precision, and you're going to understand why. So as you can see here, we've selected the different wells. So ViewPrint really proved helpful here. 9 wells were easily selected, and cells got printed as requested. And so here's the final result with a closer view at some of these wells. Approximately the same number of cells were incorporated into each well, thanks to the high control over resolution that laser bioprinting offers, so what I just mentioned before. Now, this feature can be used with a large selection of specific and tailored receivers, such as organ-on-a-chip devices, for example. So that's a fascinating technology, really, because it may apply to a huge number of different cell types that can be gathered onto the same chip to observe how they interact and interfere with one another. So, in other words, thanks to ViewPrint, the instrument can adapt to a specific chip, which is a real advantage for those of you who have already developed your own device. And so this here, what you see on screen now, was taken from a very interesting 2019 publication from Ye et al. About a human glioblastoma on a chip using an in-house bioprinter, where the chip itself was bioprinted. And so this could perfectly be replicated with NGbr, yet benefiting from the exclusive laser bioprinting technology for even higher resolution and precision. And so that for multiple cell types, including, for example, immune cells. So fortunately, we're running out of time, but for those of you who are interested to find out more about this, we highly recommend this publication from 2019. So go have a look. Another type of chip that Bioprinting can help with is MEAs. So that stands for microelectrode array. And here again, you can work with either single cellular cultures or multicellular models, and with a decent variety of cells. So most frequent are cardiomyocytes or even neural cells as part of brain-related studies. But the point here is that cells can form actual networks and get activated through electrodes at a specific time. So you could choose to activate them all, or activate only a bunch of them, or only a single spot at a time. Really, really interesting stuff. We have a lot of questions on this in terms of what the instrument can do, what specifications are there. So in terms of specs, you can work at a very small scale. As you can see here, wells of 250 microns aside, printing either a couple of cells or many more per well, depending on the resolution that you need. And that's another question we often have, like what's the recommended distance between droplets? It's, well, typically from 50 to 100 microns. And droplets could have a minimum volume comprised between 50 to 100 picoliters. So that's it. This is the end of my presentation. Thank you all very much for watching. I am now going to pass it on to my colleague, Michael Garcia, who's going to tell you more about tissue morphogenesis studies, as well as 4D bioprinting applications. So Mika, all the way to you.
Thanks, Antoine. Hi, all. I'm Michael, Business Application Manager here at Poietis. So part of my job is to manage R&D projects with industrials, but also with academics through European projects. Other part is to understand customers' needs and then lead related applicative projects. In the previous webinar, I discussed the notion of 4D bioprinting and the importance of cellular organization through patterns when designing tissue models. Today, I would like to go into more details and show you the direct applications that laser technology allow. Laser bioprinting is a nozzle-free technology known to be resolutive, allowing excellent cell viability while preserving cell integrity. But it is also very fast. This printing speed is possible because of the scanning mirror. The small scanner located on the optical path of the laser allows to move the beam quickly and precisely to various positions on the ribbon. These positions are the ones we have previously defined as pattern when creating a CAD file. For each of these positions, a drop is ejected, forming the desired pattern. On this video, a pattern of about 400 droplets has been printed. You can see how fast it goes. Therefore, it is easy to generate self-pattern in high throughput in a precise and reproducible way. You can print different cell types, as is illustrated here. This ability to co-culture different cell types is very powerful, especially for cancer research, as we know that tumor cells make constant use of other specific cell types in their surrounding to progress in their behavior. And as explained previously by Antoine, thanks to the microscopy and the Bioprinting program, it is possible to let cells mature and at several days interval, visualize the evolution of the sample and choose to print new cells on areas of interest. Thanks to the laser technology, this type of study is quick to set up and can generate a large amount of data in reductionist 2D assay and, of course, in 3D. Placing cells in 3D versus 2D increases the degree of interaction with their immediate surroundings. So cells respond to the ECM, their migration is affected, different intracellular pathway can be activated, also different gene expressed, and icon sense 2D could be perfectly be carried out by comparing cells printed over a layer of matrix to cells printed in sandwich between two layers of matrix. Different cell layers can also be generated and studied as illustrated here. Two fibroblastic populations were printed with laser in this example, and in between layers of collagen were printed with the microwave. Confocal imaging was performed to visualize them. The spacing of these patterns in Z can finally be modulated by the thickness of the material layer printed with the microwave. So here you can see the precision of the cell positioning on this video. Co-culture and cellular influences can therefore be studied in 2D and in 3D. Laser bioprinting also allows creation and maintenance of more complex structure in high throughput, like spheroids. So spheroids can be obtained in a pseudo 2D matrix as shown on this image, or in a 3D matrix also. The process is fast, similar to what was illustrated on the video before. The only difference is that we repeat locally several prints of few seconds to concentrate more cells. And by playing on the local cell concentration and also on the matrix environment, you can induce the formation of a large quantity of homogeneous size spheroids. And again, you can do co-culture. As illustrated on this picture, you can visualize in the bioprinter your spheroid at various stages of maturation. This with the integrated microscope Antoine presented to you. Then you can select easily areas of interest. You can do it manually through viewprints or automatically via the CAD software. And then you can print a new cell types. So in this case, it was over a pattern, but you can print new cell types at different areas of interest. And still, it's interesting in oncology areas where you could create spheroids mimicking primary tumor in high throughput. And then a long time you could print new cell types like fibroblasts, for example, and study epithelial to mesenchymal transition of tumor cells at the age of tumor mass. As previously mentioned, it is possible to perform high content studies on cell migration. We perform that for different kind of application here. In these morphogenesis studies, we analyze different variables, such as the influence of various matrix environments, various cell types, but also the influence of various cell organizations and patterns, as illustrated here. Let's take these two first organizations, namely printing on a homogeneous layer of cells or printing in uniformly distributed patterns. On these pictures, what we see is keratinocytes. The objective was to obtain an homogeneous layer. The results show that with laser, there are two ways to achieve this. Either by printing uniformly distributed patterns and obtaining an homogeneous layer at day 3, or directly printing an homogeneous layer of cells with closer patterns. Only the chronology change. And in the design of a full thickness skin model, the keratinocyte deposition step is very important. These cells must form an homogeneous layer before the passage in the hair liquid interface, marking the beginning of the differentiation and allowing a good stratification of the epidermis. Here we see the difference between a model where the keratinocytes were printed with an homogeneous layer. On the left, cells are confluent and organized in 2D, and a model where the keratinocytes were manually deposited on the right. The keratinocytes were deposited with pipettes, and here you can see that the sample presents empty zones and 3D areas where keratinocytes are already differentiating. And here is the workflow of the production of our skin model. This phase here that I mentioned earlier, where you print keratinocytes, this phase can thus be modulated chronologically with our technology in order to accelerate or slow down the maturation of the tissue and make various keratinocyte function emerge or not. So thus, Such a reductionist studies on patterning can easily allow you to improve the protocols for the development of tissue model like us. And as I said before, we can conduct also high content studies on the cell migration and on network formation. And here, in our case, we have performed this type of studies for various fibroblastic cell types in order to study the migration in the dermis and the influence of the remodeling of the matrix. This was the subject of the thesis of one of my students, Camille, who did a brilliant job. An article is in the process of being submitted, so I can't present it now, but I hope to be able to do so very soon. However, I wanted to show you the kind of data you can generate by coupling bioprinting manufacturing with proper 3D analysis, like light sheet imaging. You can appreciate here cell migration over time in a 3D matrix. What we look at here is fibroblast migration inside the collagen matrix a long time, and we can precisely track patterns evolution and cell migration from day 0 to day 5 after printing. Not only cell migration can be studied, but also the influence of cells on the matrix environments. Here, using a light pattern, we were able to study and observe over time the influence of cell migration on the organization of collagen fibers inside the matrix. We see here a very marked bundle alignment between the closest patterns, but also alignment of thinner fibers between the two lines. This type of study was recovered and used by another student in thesis with us, Arthur Douillet, who works on modeling. In silico cell models are more and more used as an alternative to in vivo and vitro models. These models allow us to reproduce the cellular and molecular dynamics, enabling to accelerate research. This approach is quite complementary to high-throughput screening. It is based on the development of algorithms that are fed by experimental observations. So to develop these algorithms, a large amount of experimental data are required. Moreover, the precision with which the experiment will be conducted will have a direct influence on the accuracy of the algorithm. A high fidelity is needed, and exactly what our bioprinter allows. So by retrieving data from the fibroblast migration studies illustrated above, Arthur was able to develop a model that allowed predictive modeling of events. His work led to this workflow illustrated in this video. Namely, he used experimental post-printing images taken from NGb-R by the microscope. Here you can see the patterns of fibroblasts printed on collagen. And an in-house software allows to recover the precise position of each cells, what you saw just before, and these positions are transferred to the modeling software Arthur developed. The software then ran and used a different algorithm developed to model migration events of cells, interactions with matrix. It's what you see now. And the more the matrix is remodeled, the more it tends toward red. And with the end, we can compare the results of this modeling to what actually happened in vitro. And so here is a summary of this workflow. You have the experimental data on the top and the data obtained from the simulations on the bottom. We can see how accurate the model can reproduce events obtained in vitro. In summary, high-content cell patterning offers various utilities both for tissue material fabrication, adjustment of experimental protocols, development of in vitro models, but also the development of alternative models such as in silico models. Not only cell patterning is interesting, but also material patterning. Bioprinting offers the possibility to pattern various materials in 3D and thus create microenvironments for the development of more complex in vitro models. Here I took the example of an experiment that I did myself. I wanted to test the patterning of alginate. So I used microvalve heads, one loaded with CaCl2, the other with alginate. So here you can see the CAD design, and by co-printing locally with these two modules, I generated the adenoid patterns visible on this picture below. On the right, you can see the geometry of one of these patterns observed from the side. And then I wanted to see if the generation of such a microenvironment could have an influence on the development of a skin model. Commercialized skin models all have a flat dermal epidermal junction interface. So this is not the case in vivo, where there are microvilli at these interfaces. And this structural organization is important for various functions and also cellular exchanges. I wanted to see if by patterning alginate over a cellularized collagen matrix before adding keratinocytes could influence the organization of the epidermis and this junction. Here are the results. So the epidermis is not perfectly organized, as you can see. Adjustments are to be found for sure, but I just wanted to illustrate for this experiment that it is possible to create microenvironments in an automated way with our system, and that bioprinting is a really interesting tool to develop but also complexify tissue models. So this is the end of my presentations. Thanks for attending. Tonya, back to you.
Perfect. Thank you so much, Mikhail. At this point, we'd like to just launch our last poll before we move into the Q&A dialogue. And so again, just looking for some information if you'd like us to follow up with you to learn more about the system specifically, or if you were just here to learn more about some interesting technology that we have here at Synteca. And again, if anyone has questions, please feel free to put them in the Q&A dialogue box, and I will work through them with the guys in the time that we have left. So we've got about just under 20 minutes left. So we've got lots of time for some questions. So feel free to think about what we've talked about and ask any questions that you may have. Okay, I'll give everyone a few more minutes or seconds just to answer the poll. Perfect. Thanks so much for that. And now we'll move into the Q&A session. So the first question that we have is, who makes the bioinks or the ribbons with the cells in them, and how difficult is it to make them, and what is really the compatibility with different cell types? And I know that Antoine touched on this a bit. I'm going to take a stab at answering this one, and then if the guys have anything that they'd like to add, I'm happy to open it up to them as well. So traditionally, the term bioink and ribbons have really been used for more extrusion-based bioprinting systems. With laser-assisted bioprinting, as Antoine and Mikhail showed in this webinar and in our previous webinar, the cells are really just contained in the cell media alone. And so there's no need for other extracellular matrix compounds or materials to be incorporated for the fabrication process. Or for the printing process with the laser-assisted bioprinting. You would print those onto your matrix using the extrusion and the inkjet heads. So when the cells are being prepared, they're typically prepared in the cell media alone and printed with the specific patterns using that laser head of the NGb-R system. The cell media is very simple and easy to prepare. It's the normal media that the cells will be contained in. And as Antoine showed on an earlier slide, the cells are simply pipetted onto that metallized substrate slide. So this is a small circular slide. The media is pipetted on and basically spread gently over the surface of the substrate, that metallized substrate, and then that's put onto the laser-assisted bioprinting head. The slides themselves can be purchased from Poietis directly with the metal spread on the surface. They can be prepared by yourselves, but you'd need a sputtering gun to apply that metallized surface. And so with different service packs or starter packs coming from Poietis, you have those already prepared and you simply just pipette the cells within their media on top of them, and then you're ready to do bioprinting. Okay, so just taking a look at some of the other questions. How big of a cell cluster can be handled by the system? And I'll leave that for either Antoine or Mikhail.
Sorry, so regarding the question, so meaning how we can manage maybe the size of the cluster?
How big of a cell cluster could be handled? So I guess in terms of number of cells or microns in size?
So it really depends. So just to make you understand how it works, so usually by controlling the laser power, the energy of the laser, and the volume and the cell concentration, we can generate droplets of different sizes, so clusters of different sizes. It can start from around between 1 and 3 cells, and we can go to hundreds and thousands of cells. So it really depends on your workflow, but yes, we can generate patterns of different sizes, and there are different ways to do that. Or by printing a single droplets. Printing a single droplets, usually you can print from 1 to 100, 200 cells. And then if you repeat the printing of many droplets at the same location, like for spheroids, you can go over thousands of cells in the same spot.
Perfect. And so spheroids and organoids you'd have the ability to have a larger number of cells to be able to create such structures, yeah?
Yes, and you can control precisely the quantity of cells. And so that's why, and in the example that I presented before, we've got spheroids with really good precision regarding the size, with the same size, with really homogeneity.
Perfect. A question a little bit going back to the basics of the system, and perhaps I'll take a stab at answering this one first, and then you guys can add in afterwards. It was just a question of, can we explain again what we mean by 4D printing? And so when we think about printing, we obviously think about printing in 3 dimensions. So we use that integrated computer to take our cell patterns that we outline on the CAD software. We may integrate layers of collagen or different extracellular matrix compounds, different materials to make a 3D structure. That 4th dimension comes in terms of time. And so when we're looking to fabricate a tissue, we don't necessarily need to fabricate every little detail of that tissue, but we need to understand the cells that we're printing, the environment that they're in, so that they will develop into the structures that we're looking to fabricate or looking to print. So again, in 4D printing, we're printing something in 3 dimensions, but knowing that there's an interval of time which has to take place to get us to the end result that we're looking for. I don't know, Antoine or Mikhail, if you want to add to that.
Well, that's pretty much it. You did a great job, Sonia. So it's basically taking time into account when designing micro patterns of cell droplets, and in order to gain control over tissue morphogenesis, or at least to help induce key biological processes and functions in whatever tissue we're bioprinting.
Perfect. Another great question that I know many people have and they're thinking of, so thank you for asking it, is how do people get these cells? And I'll take a stab at this and you guys can expand on it as well. There's different places to get cells from. Obviously, you can be growing them and culturing them yourself, accessing different pluripotent stem cells from commercial sources as well. And then I know at Poietis and Syntica, we're working on forming a network of people that we can recommend and kind of connect you with as well to help you source those cells. And the team at Poietis has extensive experience in working with the cells and can help kind of guide you in that direction. So I don't know, Antoine or Mikhail, if you want to add to that.
I think that's all there is to say.
Yeah,
So
I wasn't sure if you had specific examples of where you've gotten cells from in the past or anything like that.
No, that's exactly what you described. I mean, you can get cells and source them from many different places, and I guess it's very similar across Europe, North America, and any other country. Yeah.
Perfect. A question about pluripotent stem cells. Is there any literature or publications using them with the NGbr system that you're aware of?
So actually not. The cells that we presented before are cells that we print for one of my European projects on pancreas. So we are actually working with different kind of pluripotent stem cells, but no, there is no actually publications on that. But I hope in the next few years, yes.
Fair enough. Perfect. And there was another question as we went through that I've answered privately, but in the transcript, I will get the references that Antoine referred to throughout the presentation, and we'll put those in so everyone has access to those links so they can, if you choose, look further into the publications that Antoine did discuss in his portion of the presentation. I'm unsure which one of you will want to answer this question, but I'll take an initial stab if I can. Can you elaborate about the effects of laser-assisted bioprinting on the stress and cell viability? So this is something that we talked about during the first webinar quite a bit in terms of the benefits of using the laser-assisted bioprinting system, head on the NGbr, is that the forces that are typically required to extrude the bioinks from extrusion and bioinjection heads isn't necessary with a laser-assisted bioprinting. So with the cells spread over that metallized substrate, there's simply a laser light hits the metallized substrate, the droplet forms, and it shoots up towards the plate that you're printing on. You would have previously printed something soft or something that's not going to damage the cells, such as collagen, for them to adhere to and not be damaged as they move towards the surface. But the traditional shear stress and pressure that's required with normal bioprinting isn't in play with the laser side of things. So there's reduced stress on the cells. There's less complication in terms of the media or the material or the bioink that you need to formulate to try to reduce that. And therefore the viability increases as well. Antoine, anything that you want to add? I don't remember what the % viability with the laser-assisted bioprinting is. That's a number that escapes my head.
It's close to 95% actually, and as you explained, I mean there's literally no shear stress with laser bioprinting because it's a nozzle-free technology. So that's the whole point of printing cells with laser is that you can bypass and avoid all these pressure and stress problems, and that's why the cell viability ratio skyrockets. Yeah.
Perfect. Excellent. And it looks like there's an add-on question there. Is there any heat generated when the laser hits the metallized substrate and therefore affecting the cells?
Yeah, well, I can understand where the question comes from. There is absolutely no problem with heat whatsoever. The laser beam itself never touches cells. This is something that people are usually afraid of, and they think this might at some point impact the viability or the cellular integrity, but it's definitely not the case. So we're just using laser beams to create kind of a cell ink bubble, right? So basically using pressure with the ribbon so that a jet of cells in their media will be ejected from the substrate to a receiver. So there's no problem with heat at all.
Perfect.
So
Go ahead, Mikael.
I just something. So the heat of the laser that you can imagine is absorbed by the gold layer on the ribbon. So that's why this layer exists, to prevent for this kind of effects. So there is no heat on the cells, just on the ribbon.
Got it. Staying on the idea of temperature, with the integrated robotic arm, is there any heat generated during the fabrication process from that arm kind of moving and doing all of the different steps? And would that affect the temperature of the environment within the system?
Absolutely not. Yeah, so no problem at all with the robotic arm. Yeah.
Perfect. Excellent. Question, any benefit of using laser-assisted bioprinting over sound wave droplet formation?
Well, could the person specify whether it's in terms of cellular viability, or, I mean, you know, what do they want to compare it with?
Sure. Dr. Kep, if you can pose another question just to clarify, I'll jump back to it in just a second. I'm just scrolling through and looking for another question. Sorry, I'm just reading one to make sure that I understand it.
There's one from MEBServe
Sure.
about well plates that
Sure.
we could maybe address.
Yes, that would be
So
great. Thank you.
yeah, so yeah, MEBS. So far the NGbr system is compatible with single, 6, and 12 well plates only. But we've been discussing with a few people recently that are interested in using 96 well plates with the instrument. So technically, it is possible to use it. There's absolutely no problem with the technology itself. The only limitation is the distance from which we're going to print cells with the laser head. Because with 6 and 12 well plates, I mean, the well is big enough so that the laser head can literally go inside. And so we're printing from only a couple of millimeters away. But if we want to work with, say, 96 well plates, for example, we'd have to print cells from a bit further away. And so we're currently in the process of evaluating whether this distance would have an impact on precision and resolution. So we're pretty confident that we will at some point be able to open it up to 96 well plates. Yeah.
Perfect. And then jumping back to Dr. Kep's question about laser-assisted printing versus sound wave droplet formation as it relates to cell viability and the precision of the printing.
Okay. Well, to be honest, I don't know what the viability ratio is with sound wave bioprinting. So, you know, I don't want to answer and maybe give you some wrong feedback. All I can speak about is the technology we have. And I do believe that in terms of viability, it's really, really interesting. But yeah, it's really tough to discuss about a technology that I'm not
Sure.
an expert of. Yeah.
And maybe
Sorry.
that's just a conversation that we can take offline and have a more in-depth conversation to understand
Oh yeah,
better
absolutely.
the other technology as well. So questions coming back to how the printed tissues have been used in the past. For example, have they been used for drug testing, and have any of the disease models which have been printed been used to screen drug candidates, for example?
Oh yeah, absolutely. And that's I don't know if that person was with us during the part on liver tissues.
Mhm.
That was an illustration of that. So basically, yes, bioprinted tissues can be used for a bunch of applications, and one of them is toxicology, drug screening, and so on. Yeah, absolutely.
Great. Another question, is there any need for any type of polymerization, sorry, I'm having trouble with that word today, printing such as UV light? I can take a stab at this answer first. So there is the option, if you're using something that needs to be UV cross-linked or polymerized, there is the option for a UV multi-wavelength device to be integrated into the system, so that robotic arm would simply take the matrix that you're printing onto over, and it can do that UV exposure if needed. I know there was questions during the first webinar about using heat, for example, to cross-link the collagen. And so with that, the team has just been taking the plate out, throwing it into an incubator for a few minutes as long as is needed to do the cross-linking, and then placing it back into the instrument. So there's different techniques that may be used, but if you are using UV light, there is a possibility to integrate that within the system as well. Okay, so with that, we've really reached the 60-minute mark. Again, if you've got additional questions as I'm finishing up, please feel free to answer or type them in. We will address them in that transcript and get you answers. Whether they're in the transcript or not, we will answer you privately with those. So to be respectful of everyone's time, we'll wrap things up. But again, we will get that transcript out to you in the next few days, but please feel free to type in more questions as I'm talking. We'll be happy to address them. I do want to take the time to thank Antoine and Mika for their help in the presentation today and joining me to help address many of the questions that you have. I do trust that we've been able to provide you with some exciting information about the possibilities of using 4D bioprinting in such a wide variety of applications using the NGbr system. If in the days and weeks to come you have additional questions, please don't hesitate to reach out to us. I'd be happy to try to answer them directly myself or get answers from Antoine and Mika as well. I'd welcome the opportunity to discuss any research questions that you have and how the system could help you move your work forward. And again, thanks to everyone for joining us today for the webinar, and we do look forward to seeing you at a future Syntica instrumentation event. Thanks so much and have a great day, everyone.